Okay, so we're going to go ahead and design a glulam beam. And this glulam beam is about 48 feet long. If you look at the plan view, looks like a roof beam. It's 8 feet apart on center, and it's 48 feet long. And the dead load is given 31.25 pound per square foot. The snow load is 93.75 pound per square foot. If you multiply by the tributary width, then you're going to come up with 1,000 pound per foot. So the beam is basically has 1,000 pound per foot. And we're going to design this for a 1 hour and 2 hour fire rating. And first let's design it, then we go through all this stuff. When we design a beam, especially timber or any other beam, because the beam is long, obviously the fluctuator or bending moment will control. We design for bending, and we check it for shear, we check it for deflection, and we check it for bearing in timber cases. First, I'm going to go ahead and calculate the bending moment. You all seen the formula from kindergarten. The maximum moment for a beam like that is W L squared divided by 8, and our W is 1 kip per foot, and time 48 square, and that's a kip per foot, by the way. Divide that by 8, that should give me and let's multiply that by 12, and I'm going to go ahead and say 288 foot kip time 12, give me an inch kip, and that should give me about 3456 inch kip. Now remember, this is a maximum moment due to the loading. So I'm just going to go ahead and write this max moment due to load. Then we're going to compare that to capacity of the beam. What is the maximum capacity bending moment for that beam? Is he going to make it or not? Let's just go ahead while we have calculate the maximum shear. Vmax is going to be, obviously, looking at the bending formula equation, is WL divided by 2. And W is 1 kip time L 48 divided by 2. That should give us 24 kips. Perfect. In DS table 5.3.1 and 5.3, 5 and 5.36. We have F prime B is equal F of B, CD, CM, CT, CL, or F prime B is equal F of B, CD, CM, CT, CV. So basically the lesser of these two, you could say F prime B is equal to FB, CD, CM, CT, CL, or CV, and the lesser of the two. And I just separated both of them. And because this problem says, okay, this is 8 feet apart and laterally supported, and therefore our CL is equal to 1 here, because there's a lateral support, there's something on top, and it's like a diaphragm or whatever, and maybe a floor beam. And so you don't have to write CL. Then therefore we're going to say, okay, this is going to be the lesser of the two. This one going to control right here. This will control since CL is equal to 1. But going back to the adjustment factor, I'm going to come up here. Let me separate this. We have, actually I'm going to write down here. CD is equal to 1.15 because we have a load combination between snow and dead load, so CD got to be 1.15. Pay attention to these in that section. I got them on a board right there. Take a look at it. And then we have CM, which is the moisture contact is good, so that's going to be equal to 1. And CT is also is equal to 1 because it's in the inside condition, so no problem. So from NDS table, 5A, F of B is 2400 PSI. And then we're going to go ahead and write the whole thing back in here. But we know this one. We know this 1, 1, 1. So this is a 2400, 1, 1, 1. This we don't know size factor. What we're going to do, we're going to go ahead and make an educated guess, 0.82, 0.8, 0.85, something like that. Let's go ahead and say, okay, assume CV is equal 0.82, and then we can come back. If it's less or more, we can make an adjustment. So I'm going to go ahead and say, okay, F prime B is equal 2400 time 1, 1, no, I lied. 1.15, 1.15, now 1 and 1 and 0.82, and that should give me, and what I have is 2263 psi. Okay. So now we have that, and we know bending moment. Look at that equation. So I'm going to say require suction module is equal M divided by F of B, and our M came out to be, or not to be, 3456 inch cube, and divide that by F of B, which was 2263 psi, and now we have 1527 inch cube. Now, since we know the suction module, we can go in a table 1C. Interesting part, we go to section 1C, and we're going to say, okay, if we try, I'm going to pick 3 of them out. Try 6 3/4 by 37.5, and that will give me suction module of 1582. And because we're doing a fire rating, you really want to make this number as big as possible, but not too big. But because we know beam, the taller is the moment inertia, all that stuff, you know that. So let me just go ahead and put 3 try out. Try 1 is going to be to the table 1C, and our suction module is 1527. And from that table, we selected 3 different ones. I can go with the 6 3/4, 37.5, which section module is this, and 8 3/4 by 33, section module 1588, 10 3/4 by 30, section module is equal 16113. And the reason I picked 3 of them, because we're doing a fire rating, it comes in handy when you look at back what we had. And all these 3 right here, all 3 of them, they are bigger than 1527, so they basically pass the bending with flying color. And we're going to check for shear, and we're going to check for deflection and bearing. We're just going to use this one, but you can go ahead and practice with this 2 on your own. Anyway, so that was the bending check, and we passed the bending check. But since we guessed that CV is equal 0.82, let's go ahead, calculate CV. Again, calculating CV is going to be based on the size that you selected. And I'm going to just do this one, and then you can follow the same step, do both for the same thing here. And if we look at the NDS, and that's a section 5.3.6, they have the CV equation given like here. So this is the equation, and for a 6 3/4 by 37.5, CV is equal 21 divided by 48 is the length by power of 1 over x, and x is given in the S, and that's 10, so it's 1 over 10, and 10 time 12 divided by d. Our d in here is a 37.5. and by 1/10, and also it's 5.125 divided by b is a 6 3/4, and by power 1/10, and our CV comes out to be 0.799, which is less than 0.82 we picked. So now you go ahead, and while you're doing this work, if you're interested, do the CV for this one and this one, see what you're going to get. And while I do that, I'm going to erase this side. So now we selected this size, and we found out that this beam that we're selecting is 6 3/4 by 37.5, and we're going to use the section module of 1582. That's what for that beam is, which is S is equal to BD squared divided by 6, or you can pick that from a table. So now we have that. We're going to go back and find out, see what is the stress due to the load for this beam size. Our moment we calculated, which I erased, you have it, or go back, you can see it, and that was what? That was 343,456 kip inch. Let's make that to inch pound, so I'm going to add a 0 to it, so that's an inch pound, and divide that by 1582 pound per inch square, so unit can work out. And now my stress due to the load, it's going to come out to be 2185 psi. Okay, so that's the stress due to the load. Now we got to compare that to the capacity of the timber of that size. And how we do that, we already know the equation. F prime B is equal, and right there. So we're going to plug in all the number. FB was 2400, and that was 1.15 times 1 times another one, and this time our CV came out to 0.799. 0.799, and now F prime B comes out to be 2205. 2205 psi. That is the capacity, which is bigger than the load, and 2185 psi, and we okay right there. Remember, that's a capacity, and that's due to the load. You always want your capacity of the beam be stronger than the load you put on. If the load is heavier than your capacity, then your beam is going to break. So now we're going to check for shear. We did that. Let me switch color here. Check for shear. This mark is headed. Yes. Same table, 5.31, if you remember. We're going to have a shear capacity F prime via X is equal F of V times the adjustment factor were CD, CM, and CT. And this shear is from table 5A. This is a table 5A. That's where I come from. So F prime via X is equal, and that table from 5A is 265. You see that on the board. 1.15, you already know that, times 1 times 1. So F prime via X comes out to be 305 psi. So the capacity, the shear capacity of the beam comes out to be 305 psi. But we're going to compare that to the shear stress due to the applied load. And you know, shear stress is equal to 1.5 V divided by A. We calculated V from previous, which was 1.5 times. That was 24 kip, so, or 24,000 pound. And the area for this right here, if you look at the table or calculate it, the area comes out to be 253.1. And that's the area of 6 3/4 by 37.5. So the shear due to the load comes out to be 142 psi. And you can see it's way, 142 is way less than a capacity. Capacity is 305 psi. This is the capacity. So you got a capacity and then you got this, so you're okay right here. Before we check for deflection, we're going to find out what is the margin of elasticity E prime exit is from same table 5.31, and that's equal to E time Cm Ct, which basically it's a 1 and therefore is equal 1,800,000 psi. And if you go to the beam formula, deflection is equal, this is a deflection for total load. And if you do live flow, if you had live flow, which you don't have here, then you could do live load deflection, then you do dead load deflection or total load deflection. And we're going to do, probably in this case, we're going to do snow load deflection, make sure we meet the code. And from beam formula, that is equal 5 times W L by power 4 divided by 384 EI, which is equal 5 times 1,000 times 48 by power 4 times 12 by power 3. Divide that by 384 times 1,800,000 times I for this from the table, it comes out to be 29,660. Okay, so let's look over this. We know the load, we know the length. We got to convert them to an inch. We time by 12 by power 3. If you say why not by power 4, because you already have a foot down here. This is a 1,000 pound per foot. So that's what cancel out. That's why you go with 12 by power 3. And then you have this, and this is from the table for this size. And this comes out to be, the total load deflection comes out to be 2.24. And that should be, really, that 2.24 inch should be less than L divided by 180. Depending on the code, some code might say L over 240, depending where in the country you are. So let's just go with L over 180, which is equal, L was 48 feet. Let's convert that to inch divided by 180, and that will give me 3.2 inches. We okay. So we check that deflection. And let's go ahead, by code, we're going to check deflection for snow. Let me change color. Deflection for snow, same equation. And it's going to be, instead of going through all those calculations, I'm just going to take a shortcut. Or you can go ahead and do this, same thing. Remember, this is a 750, that's a 250, the total was 1,000. So this deflection total was for 1,000, but I want to get deflection load for 750. So let's take a shortcut. So I'm going to say, okay, is equal 750 divided by 1,000 and time total deflection. That's one way. Or you can go through that. It's up to you. And this is easier. So that's a 3/4 time 2.24, and that should comes out to 168. And that should be less than L over 240. Let's find out. 1.68 is less than, L is a 48 times 12 divided by 240, and that will give us 2.4. Okay, we passed that. So we passed, we designed for bending, we checked it for shear, we checked it for deflection. The last check we're going to do is bearing. I'm going to go ahead and erase this, and we do bearing. Okay, we're going to check for bearing. The bearing equation from 5.3.1, same table as this. Per compression perpendicular to the grain comes out to CMCT, CB. All these are 1 because it's laterally supported, temperature and moisture. So, and this comes from a table, what was it? Table 5A. 5A, so that's equal, came out to be 650. 650 10 bunch of 1. And that's equal 650 PSI. It's a stress. So now we're going to say required area is equal reaction from this right here, which is basically WL divided by 2, which is equal 24 kips. And divide that by the stress F prime compression to the grain. So that comes out to be 24,000, all right. Divide that by 650, and that is equal so that's equal 36.9. Area is equal 36.9. That's an inch square. Now we want to say what is the required bearing length, LB. LB is basically, hold on, I don't have it here, I had it here. Okay, so if the bearing length, you know what I'm talking about, just put this thing on. And the required LB is equal 36.9, divide that by the width of our beam is a 6 3/4, 6.75. So that is equal 5.47, say 5.5 or 6 inch. It's up to you. So that's our bearing. So now we're going to say, okay, this beam is okay, designed for use 6 3/4 by 37.5. So the beam, if you use this beam, is completed. It will stand that load. Wait a minute. The question says, what about for 1 hour rating, 2 hour fire rating? So let's check to see if this is going to make it. And I'm going to erase this. We go to NDS table, section 16.22. It's a good chapter, you should read that. It says for 1 hour rating, when a fire happens, we're going to have this situation. This is the beam, basically. Okay? The beam, it's going to fire happen. It's going to burn from outside here, bottom of outside, inside the room here. And the top doesn't burn because there's a floor on top of it. So it's protected from here. So that's not going to burn. If this is the beam itself right here, if we continue like that. And it says for 1 hour, this should be right here. This should be 1.8 inches. And we're going to go ahead and resize our beam. Take that 1.8 out here. So we're going to say, okay, our width of the new width of the beam, it's going to come out to be 6 3/4, 6.75, minus 2 times 1.8, because this is going to be new width. And that's going to come out to be 3.15 inch, 3.15 inch. And then the height, the new height is going to be from here to here without the burn area. So the length, or D, what we call it, it's going to be 37.5 minus 1.8. And that should come out to be 35.7. So now we're going to find out the new section module. Based on that, section module is BD squared divided by 6, 3.15 times 35.7 squared divided by 6. And that comes out to be 669.1 inch by power 3. So that's what we're going to have. Then same chapter 16 is give you this equation. It says the capacity of our beam in a fire, F prime B, I explain that in a second, hold on. They have this multiplier 2.85 time F of B time CF CV CL, basically lesser of this two, which we already talked about. The lesser of the two. This is 1 anyway, so it basically is CV control. And so our new F prime B, just bear with me, it's equal 2.85 times 2400 times 1. I think the size factor came out to be, this came out to be 0.799. So this new capacity, it's going to be 6839 PSI. This is bigger than before. Wait a minute, what happened? So the whole idea says when we design this beam, the way we design it, the real capacity is probably something like this. But we put factor safety and all that stuff, and we're going to say, no, the capacity was what we had before. I don't know what the number was. So the code says, no, it really can stand up to this much since it's going to be for 1 hour during fire and emergency. It will give enough time to get out. So now this is our new capacity. And we look at it, we say, okay, this is stronger than before. So 1 hour, it passes with flying color. But let's figure it out mathematically that we are correct, that it does passes in. I'm going to go ahead and say our allowable moment, or we can do stress, just moment. It is equal 6839 pound per square inch multiplied by the suction module. You know the equation for these, right? 669.1. That's an inch cube, and I'm going to end up with the inch pound, which came out to be 6,974.9 inch pound. This divided by 12 divided by 1,000, and make it an inch cube anyway. So inch cube comes out to become 6,575 inch cube divided by 1,000. And our moment capacity, which we wrote down here, was 3456. So we make that no problem. So we good for 1 hour fire rating, or for 2 hours. 2 hour fire rating, and let's work on that. And if you look at the code, which I got on the board, before I go on, there's a you can use TR10 table. You can download it from Google. You can go to the end of the page, and there's a table. Instead of going through all these calculations, you can use a table. But let's go through the calculation anyway. It doesn't take much. That way you're more sure. You use it basically, line up, you find a number, this become 1. And then for this one, you use 2 hours, see what the stress ratio is going to come in, and you multiply by stress ratio, see if it's going to work out. But I want to do it the old way. So our new for W going to become 6.75 minus 2 times, for 2 hour rating was 3.2 inches. Which basically there's nothing left at the beam, 0.35. You already know it's not going to make it at 0.35 inch width. And your D is going to be 37.5 minus 3.2, and that will give you 34.3. Your suction module is equal BD squared, so it's a 0.35 times 34.3 squared divided by 6, and that comes out to be 6862. And now your allowable moment is going to come out to be 68.62 times the stress was 6839, and that gives us comes out to 469, which is less than moment due to the load, which was 3456. That's a moment due to load and moment capacity after 2-hour rating. And you know it's not going to make it, no good. It's going to fall down. It's not good for 2 hours. And that brings us back here. Remember at the beginning I told you if you select these sizes, and this is going to have some wood left on it. Try this one, see if this one will make 2-hour rating or not. That's on you. Okay, this is how it's done. I hope you enjoyed this. If you like it, please, I love your comment, and I like your thumbs up. And if you really like, you can hit subscribe too. Have a wonderful day. Take care of yourself. Life is too short. Enjoy it.